Well, greetings, everyone. Appreciate you tuning in to our monthly webinar. Hopefully you are here for the July webinar for the American Segmental Bridge Institute. We have a good presentation today, providing insights on concrete segmental bridge construction. I'm Greg Freeby, the Executive Director of the American Segmental Bridge Institute. You see my email address there on screen. If you need to get in touch with me, certainly encourage you to reach out to me, and also encourage you to follow me and the American Segmental Bridge Institute on LinkedIn if you're not already. It's a great avenue we're using to provide not just announcements about training events or educational opportunities like this, but also just some information about segmental bridges from time to time throughout each month. So some quick announcements today. Our August webinar is the last Wednesday in August, which is August 31st, again from noon to 1 Central Time. And this is on the Manhattan West segmental deck cover project, which is a really interesting use of segmental bridging technology in Manhattan, New York, where they spanned over a railway yard and then built a building on top of that bridge. So I think you'll find it a really entertaining and interesting use of segmental bridging technology. So encourage you. That one's already up on the website, so you can go ahead and register today at the conclusion of today's session. Just a reminder about our latest new publication that was released, our guidelines for design and construction of segmental bridges for rail, was published in March. Encourage you to find that publication. And looks like you all are not seeing my slides, so hold on for just a minute. Apologize for that. All right, there it is now. So you're seeing the guidelines for design and construction. I'm gonna back up quick slides just to let you see visually again the Manhattan West project is our August webinar. And then I just mentioned the new publication that's out. You might want to jot that down, the title of it. You can Google search and find it, or even go to our website under the publications tab. Also coming up in August is our construction practices seminar. It's August 15th through 16th in Seattle, Washington. This is a really great opportunity to get even more in-depth information about segmental bridging technology. And I know Wade is going to mention it several times today about those opportunities to get more information beyond what's in today's presentation. We also have August 17th, the day after the seminar in Seattle. We're hosting a session of our grouting certification training. Encourage folks to register for that as well. It's open on the website. Great opportunity if you're on that side of the US, the West Coast, good opportunity to get that training in. We won't be doing another in-person session of that training. In fact, won't even be doing a remote version of that training this year. So it'll be April of next year before that next training opportunity for grouting certification. Our convention is coming up October 31st through November 2nd at the Hyatt Regency in Austin, Texas. We have a great agenda lined up for that. Registration is open on our website for that as well. So some quick instructions for the webinar. If you lose your connection, you can rejoin at any time. You'll miss the content you missed while you were away. Certificates for attendance will be issued for professional development hours. I'd ask you to wait at least a week before you get your certificate. It takes a little time for staff to run through the system to generate those certificates. So hang tight and you'll get those again in about a week. So we will be doing Q&A, hopefully with a little bit of time at the end of today's session. We may run a little long, but we'll try to do as much Q&A as we have time for. If you have any questions that come to mind as the presentation's happening, you can just type them into the questions box. We have a moderator who's going to be paying close attention to those questions, and then we'll do a live Q&A with our presenter at the end. If you're on a mobile device, you should have a little question mark in the upper right-hand corner you can use then to access the same little interface where you can type in a question. ASBI is meeting the RCEP requirements for this session for professional development hours. If you're from one of those states that requires a certification of your professional development hours, we're meeting RCEP requirements. So with that, I'm going to turn over. I'll do an introduction to our speaker and then turn over to Wade. So our speaker today is Mr. Wade Bonzen with FIG Bridge Inspection. Wade earned a Bachelor of Science degree in Civil Engineering from New Mexico State University in 1994, and then his master's degree at the University of Texas at Austin in 1996. He has more than 25 years experience in the design, project management, and construction of major segmental bridges, and he's also a registered engineer in 10 states. Wade's segmental bridge experience includes design and CEI for precast segmental bridges in Florida, Oklahoma, and the $240 million Veterans Glass City Skyway cable-stayed bridge in Toledo, Ohio. Wade's cast-in-place segmental experience includes CEI for bridges in Minnesota, Tennessee, and the $553 million Pearl Harbor Memorial Bridge in New Haven, Connecticut, the first major extra-dose cable-stayed bridge in the United States. Wade is the Vice President and Director of Operations for FIG Bridge Inspection and is based in Dallas, Texas. And with that, I will step over and make Wade our presenter. All right, great, Wade. We're seeing your slides.
All right, fantastic. Thank you, Greg. Thanks for the introduction, and thanks for the opportunity to present.
Speaking, you're probably still on mute.
No. Is that better? Can you hear me now, Greg?
Absolutely. Thank you.
Okay, fantastic. All right. Well, thanks, everybody. Thanks for that introduction, Greg. We're going to jump right in. We've got a lot to cover for the seminar today. Learning objectives, we're going to learn about the advantages of segmental construction, understand the process of precast segment casting, and talk about some of the common techniques for erecting precast segments. And we're also going to dive into cast-in-place segmental construction as well. This is sort of a primer or a teaser for the upcoming construction practices seminar in Seattle. So we'll start out with just a very brief introduction and discussion about what segmental bridge construction is, and then we'll dive into some of those more technical topics. The construction practices seminar, as Greg mentioned, is the 15th and 16th of August in Seattle. It's actually at the SeaTac Airport Marriott, so it's easy to get to. This is a in-person seminar. Yay, we're back to in-person, which is exciting. All day Monday and half the day Tuesday, so you can fly in Sunday and then fly out Tuesday afternoon, or stay for the grouting training the next day on Wednesday. We're going to cover a lot of topics during that construction practices seminar, and there's still time to register. Go to the ASBI website, asbi-assoc.org, and go to the events tab and look for seminars. Would love to see you there. So let's get into what is segmental bridge construction. So segmental bridge construction is fabrication and erection of a structural system using individual elements, which of course we call segments. These can either be precast or cast in place, and they can be used for substructures and superstructures. We're going to concentrate on superstructures today. And what's important to remember that the completed structural system acts monolithically under design loads, and that is accomplished through the use of post-tensioning to connect the segments together. The superstructure segments are essentially transverse slices of the bridge, and because of that, they're most commonly a box-shaped cross-section, most of the time with wings, if you will, to achieve the overall deck width. But U-shaped sections have been used over the years in isolated locations. And the reason that it's box-shaped is because if you can imagine taking a multi-girder bridge and slicing it transversely, that's not a very stable cross-section for handling and transporting and erecting whereas a box section has got some really good inherent stiffness and is very stable for all the things you need to do with it as it's getting incorporated into the structure. And then, of course, the primary thing to remember is, and the primary advantage of segmental construction is that the deck is cast with the segments. That is a tremendous advantage in terms of time. As Federal Highway used to describe, they want to get in, get out, and stay out. And you're talking about a structural system that allows you to get in, get out quickly because the deck is cast with the segments and doesn't have to be done at the site. And then you could stay out because it's an extremely durable structural system. So a little bit of terminology. We've got typical segments. You'll hear that described a lot. These are the box girder pieces that are in the interior of the span, away from the piers. And then you've got pier segments, which are not the precast box pier segments. They're actually the superstructure segments that are located at the pier locations, and they have very large diaphragms inside of them. That's necessary to transfer the loads from the superstructure down into the bearings or into the substructure and the foundations. So those we call pier segments, or sometimes expansion joint segments. Variable depth segments are very common. Those are for longer spans where we need to have greater structural depth near the piers. And you'll see that quite a bit, but that just means that the segment is a varying depth from one end of the segment to the other. And we have internal PT tendons, which are located inside the concrete, typically in the top slab and bottom slab, very rarely nowadays within the webs. And external tendons are post-tensioning tendons that are external to the concrete, so they're in their own ductwork, but they're inside the interior of the box girder. And then transverse PT tendons run from edge of deck to edge of deck and are there to handle loads from wheel loads and other things that are local to the deck itself. And then, of course, we won't be covering this today, but vertical PT tendons are used to post-tension segmental substructures. A little bit more terminology, zooming in on one of the segments themselves. We've got cantilever tendons, which are running in the top slab, inside the concrete of the top slab, and those can anchor either at the face of the segment or in blisters interior to the segment. We have bottom slab continuity tendons, which run through the bottom slab longitudinally and then anchor in blisters inside the box girder. And then we talk a little bit about shear keys and alignment keys. Shear keys are cast into the concrete face of the cross section along the webs and also in the top and bottom slabs. Those actually perform quite a bit to transfer shear loads across the segment joints and make the bridge act monolithically. And they also help to transfer shear locally due to bending in the top slab and the bottom slab on a kind of a local basis. So let's dive right into precast segment production. This is it's interesting to think about precast segmental bridges. Basically, these casting yards essentially are set up like factories. We want to always be thinking about production of segments in a factory-like setting, and our goal is to be as efficient and repetitive as possible with all those details. But when we're talking about precasting, modern segmental bridge technology relies on match casting, and that means that we're placing the fresh concrete for a new segment directly up against the hardened concrete of the previously cast segment. And then we have another bulkhead on the other side to form the other end of that segment. So this is really, really important because we want the segments, when we take these segments apart and move them out to the erection site and put them back up in the air, we want to make sure that they go back together exactly the way we cast them. This is a shot of some typical segment casting formwork. We have the fixed bulkhead in the back here. This forms one end of the segment. We have the core form, which slides in and out of that bulkhead and creates the hollow interior of the box girder shape. We have the exterior web and wing forms on both sides, and then we have this soffit table, which also moves in and out of the formwork, and that supports the segment weight as it's being moved around and manipulated. Typically for precast segments, we also have the pier segments that have the very large complex diaphragms in them. Those are typically cast in separate formwork and not match cast against the typical segments. There's a variety of reasons for this, and it's not always true, but that is true most of the time. The biggest reason is that these take quite a bit longer to form up and place rebar for and place concrete. And therefore, we don't want to have those on the critical path of the more regular factory-like production of the typical segments. So there's two different types of match casting techniques out there. The first one is called long line casting. And this is essentially where you set up formwork that basically shapes a very large portion of the bridge, either an entire span or an entire casting set of segments that are match cast together, or one arm of a cantilever. And this is oftentimes called the poor man's match casting technique because it is a relatively low upfront cost. And the advantage of it is that especially if you stick build the formwork at your casting yard, you can begin casting very, very quickly. It's very fast to set up, and it does require a little bit less segment handling because you're casting all the segments in the same bed and then moving them out to storage afterwards. However, it does have some downsides. It has a limited ability to handle widely varying geometry, and most bridges nowadays have quite a bit of geometric variability in them. So it's really only good for areas where you can use these formwork more than once. So if you've got a series of cantilevers that all have the same cross-sectional shapes and lengths, and it's great for that, or if you've got straight pieces of the bridge or constant curvature. The other disadvantage is that it takes up a relatively large area to do this casting because you're casting big chunks of the bridge all in one formwork system. And the basic process is that you cast segments one by one down this line, and you're match casting against the previous one, and the front end is formed with a floating bulkhead as you go. So it's a progressive casting system. All the segments are match cast together and then are able to be separated and taken out to the erection site. This actually comes in handy in some very specialized instances. This is the new I-35W bridge in Minnesota. This was a fast track emergency repair or replacement of the original steel truss bridge that collapsed back in August of 2007. The contractor was under a extremely short time frame schedule to get the bridge replaced. And so long line match casting ended up being a great solution here because they could stick build the formwork and begin casting segments very, very quickly rather than waiting for alternative casting systems to be designed, fabricated, shipped to the site, and set up. And that alternative casting system is called short line match casting. This is the second method of match casting that's commonly used. And in fact, this is actually much more common in modern segmental bridges than long line casting is now. And it's highly adaptable for complex geometry because what we're doing is we're only casting one segment at a time and then moving the segment that's done out to storage after it's been used as the match cast bulkhead. So it takes up comparatively less room, and the forms are reusable, and because of the methodology for geometry control, you can pretty much achieve any geometry of the bridge deck that you need to achieve. However, the downside is that there is a much longer lead time to get these forms designed, built, shipped to the site, and assembled. And there are only a limited number of suppliers nowadays that actually supply these things, and it can take sometimes up to a year lead time to get casting machines to the site and set up. Also, they do have a higher initial cost to purchase. They're fairly complex machinery. They've got a lot of moving parts, a lot of hydraulics to actuate the form panels and move the core forms back and forth. And therefore they have a little bit of a higher initial cost to purchase, although they are much more reusable and can be reused for other projects as well if they're taken care of. So we're going to concentrate on short line match casting in this presentation because it is much more common than the long line. And you can see here, this is a diagram of that short line match casting cell. This portion of the formwork here is where we're going to be placing the concrete for our new, what we call wet cast segment. And you can see here that the previously cast segment, called the match cast segment, is forming up one end of that segment, and the other end is formed up by a fixed bulkhead. This fixed bulkhead creates one axis of the local geometric control system within this cell, and the other axis is the center line of the cell itself. And by keeping that fixed bulkhead stable and fixed, and then making small adjustments to the alignment and angle break of the match cast segment, we can achieve casting of any local geometric relationship between two segments that we want in order to accomplish the overall bridge geometry. So it's extremely flexible to do pretty much anything we want to do. Core form system slides in and out, and then once the match cast segment has done its job, it is moved to a temporary storage spot where it is prepared for taking off to the storage yard, and the wet cast segment is moved into the match cast position for the next cycle. This is a basic casting yard layout based on the short line match casting system. Essentially, everything here is moving from left to right in this production view. So you've got rebar delivery and storage over here. You've got rebar jigs set up that are in the same cross-sectional dimensions as the segments themselves. Then you've got the casting machines. You've got the ability to move those segments once they're done out into the storage area for additional post-tensioning and grouting work, point and patch, cleaning and prep for shipping, and then the load out facility on the far right. The casting cells need to be stable and not move because they form the local geometric control system for the geometry control of precasting the segments. So casting cell foundation design is very important. We want to make sure that we've got really good ground underneath these things. A lot of times we'll actually put piling in and stuff here to keep these slabs as stable as possible and keep everything as rigid and stationary as can be. You can see that the soffit table here slides back and forth on some steel rails embedded into those slabs, and the core form on the other side also moves back and forth on steel rails. So everything is set to have that local coordinate geometry system be as stable as possible. So the daily production cycle begins with an as-cast survey very, very early in the morning. Then we'll do transverse tendon stressing in the top slab if needed. Some bridges have long enough wings that they might need some of their transverse tendon stressed before we can release the forms. Some don't. Formwork release and moving of the segments to their new positions is accomplished after that, at which point the forms are prepared for the next cycle. Everything's cleaned, re-oiled. We'll rough align the match cast segment to get the geometry very close, put our bond breaker on the match cast segment, and then install the rebar cage, move the core form in, prepare the wet cast segment for casting, and then by the end of the afternoon, we'll place concrete and begin the curing process. This is a typical 1 segment per day cycle. The reinforcing steel jigs are really important to maintain that cycle. They remove the rebar cage assembly off the critical paths. This means that the rod buster crews can work on putting those segments, cages together offline. In some cases, they can actually work ahead and really make sure that that schedule is smoothed out so that there's always a rebar cage ready to go when it's time to lower it into the wet cast position. So we're performing as much work there as we possibly can. Everything's set up with the exact same dimensions of the segments that we're, segment forms that we're casting in. The other thing that helps with this to eliminate delays is to have some additional storage for rebar cages that is offline. And again, this allows the rod buster crews to maybe get a couple cages ahead. And there's always little things that pop up. We've got a 1 segment per day target that we're trying to hit. And so anything we can do to smooth out those little bumps in the schedule is helpful to achieve that. So if we can, have a couple cages tied ahead of time, that helps with that. And then some cages take a little longer to tie because they've got more complex anchor blocks or deviators in them. And so this just helps with maintaining that schedule. So this is a shot of the short line casting bed. The wet cast segment has now been moved into the match cast position. The formwork is still not quite buttoned up here yet, but the contractor is in the process of cleaning the forms and prepping them. The fixed bulkhead is visible on the right. And the next step in the process here is to rough set this segment into its position to achieve the horizontal and vertical angle breaks that we need relative to the wet cast segment and relative to the fixed bulkhead. We'll close up the exterior forms and apply the bond breaker on the face of this segment so that the next morning we can pull the two segments apart without any breakage of alignment keys or spalls on the concrete. The rebar cage is then set into place. And again, just about everything that's going into that cage has already been installed in the cage. We'll do a little bit of adjustment to the interior core area of the cage and then slide that core form in and get that buttoned up. Then as we're performing our final setup survey, the Rodbuster crews are doing the final grading and alignment of the deck reinforcing steel. We're performing our final QA/QC inspection, and the top slab PT is being aligned in its required position. And then concrete placement's really important here, and this is a little bit of an art. We have to sort of tune the slump of our concrete for different portions of the section. These box girder pieces are being cast all in one continuous pour. So typically what we'll do is we'll cast the lower portion of both webs with a little bit stiffer mix, say in the 4-inch slump kind of range. We'll very carefully vibrate those either with form vibrators or handheld stingers to get that concrete consolidated in the bottom of the webs. And those will form a plug that will begin to stiffen as we place concrete for the bottom slab itself. And you can see here, they've got an elephant trunk set up with a hole going down through the top slab formwork to get down and place that concrete in the bottom slab. Once that's completed, they'll finish off topping off the top of the webs, close up that hole, and then cast concrete in the top deck of the concrete segment. So everything's done in one continuous pour. We don't have any cold joints. That's important not only to maintain the schedule, but also because most of these bridges are designed such that you really need to have monolithic concrete in all locations to make the rebar design work. And then the concrete and the top deck is finished either with a roller screed or some kind of a vibratory screed. The important thing to understand here is that the fixed bulkhead forms one end of the support for that screed, and the actual concrete surface of the match cast segment forms the other end. That gives you a nice, even joint here between the two segments, no bump between one segment and the other, and it allows you to achieve the very carefully set up geometry between the two segments because you're grading off that bulkhead, which is the reference point for all of the geometry in your forms. And then curing is something that we're trying to achieve about 2,500 PSI on the concrete typically the next morning so that we can cycle our forms and start the process over again. And the curing is really in a lot of ways dependent on the environment you're in. If you're in an indoor casting facility, you've got a little bit more freedom to perhaps tune the environment to what you need. If you're outdoors, you're more at the mercy of the weather. But regardless, steam curing and radiant heat are quite common, especially in colder climates. And obviously we want to have a good wet cure, especially on the top slab with, wet burlap, blankets, soaker hoses, that sort of thing. In some ways, actually in all ways, this is much easier than curing the deck of a cast in place deck on a typical beam bridge because we're only curing a small portion of the bridge at a time. And so it's a lot easier to control that environment. And then the next morning, we'll do the ASCAS survey. We do this before any start to the production on the day. Typically, we'll come in at 4:30 in the morning and do these surveys in the dark. Get those done because the crews are chomping at the bit to, verify concrete strength in the wet cast segment and get started releasing the forms and starting the cycle for the day. And we don't want any of that to happen until the ASCAS survey is performed. We're doing these surveys down to the nearest 0.001 inches both vertical and horizontal, and it's really, really important that nobody touches those forms until we get a chance to do that survey, establish that actual as-cast relationship between the two segments. And then we can, while the form is cycling, we can set up, calculate our setup values for the next segment pour. But it's really important that we do not disturb that during that process. And then it's always good to have post-pour inspections. You know, typically what'll happen is you'll see little things that happen that are repetitive issues. You might have a spall that's happening in the exact same spot on several segments, or you might be breaking the same shear key each time. You might have, you know, a honeycomb in a consistent spot. And so it's really important that we do post-pour inspections on a regular basis and identify those problems and eliminate those problems as much as possible. There's no better way to lose money on a project like this than to spend a lot of time and money on repairs. Then the segments are moved to storage. There's a whole lot that goes into this whole process. But you've got to have a sufficient amount of storage there to support the number of segments you're casting versus the number of segments that you're erecting. And it's always good to have a little bit of contingency in there for extra land if needed. The soil conditions are super important. You know, we want to make sure that we've got good enough runways out there for our straddle cranes to run around and pick up these very heavy pieces of concrete. We want to make sure the concrete segments are not, you know, settling into the ground and causing problems with that. Drainage is important. And, you know, with the advent of modern sort of inventory tracking things that are out there now, like RFID tags and other technology that's now coming into the forefront of manufacturing, there's a real opportunity here for using and leveraging some of those technologies, perhaps to keep track of the locations of all your segments. You know, in the old days, we would literally have somebody run around and have a map that they maintained of where all the segments for the bridge are being stored on the site or on the casting yard storage area. And that's a very manual way to do it, and it's very time consuming. So we're always interested to see contractors leverage some of those newer technologies and really take advantage of the ability to locate these segments in the real world in real time. Talked about storage. Storage is extremely important. Always support your segments under a 3-point storage system. This is absolutely critical that we maintain a structurally determinate storage support, because we've got 2 supports under one web wall on this side of the segment and 1 support under the other web wall on the other side of the segment. And this is absolutely, this is a top-notch, really great storage system here that they set up at Lesnar Bridge in Virginia. They've got, you know, concrete crane mats underneath here to help with some of the settlement of the soils. They've got good discrete 3-point supports with using hardwood, so it's, you know, a little bit more forgiving than perhaps a concrete block or something like that. But if you have this on 4 supports and one of those supports settled, you run the risk of basically twisting your segment, and especially over time as it sits there for weeks or months and it creeps into that new twisted position. Well, all that effort you did for geometry control and very careful surveying, you're going to be surprised when you take that segment out to the project site and it does not go back together the way you expected it to, because it's been twisted and creeped into a new position. So it's really important that all of our segments are supported under that 3-point system. And then double stacking is something that's done fairly commonly. There's a little bit that goes into it. It requires some pre-planning. You've got to make sure that the segments are designed to handle the weight of a segment sitting on top of it. And then the other thing too, from an inventory control, you've got to make sure that you're stacking these things in a way that minimizes the amount of handling and rehandling of the segments. So, you know, you probably don't want to stack segments on the bottom that you're going to need to pull out before you pull out the segments on the top. So lots that goes into that, but it is fairly common. So the casting learning curve, it's a real thing. It's unavoidable. These are complex production systems. It's essentially like putting a factory together, and with all of the little, you know, hiccups and things that happen in a fabrication type of a environment. but they can be managed, and as long as you plan for it in your schedule, you won't be surprised by it. And the key thing here is that we always want to learn from our mistakes. We want to eliminate things that are happening, especially stuff that is something that's happening over and over again. We want to watch out for those types of mistakes, and we really want to focus on quality. When you're talking about precast segmental bridges, the bridge really is being built in the casting yard. The whole process of taking the segments out to the site and erecting them out there, in all honesty, is a formality. It really is. The bridge itself is being built in the casting yard, so we want to really spend a lot of effort on making sure the quality is as high as it can be in all aspects. PT ducts are lined up, geometry control is on the money. We're not spending a lot of time on repairs and silly things like that. Post-tensioning and grouting is done ahead of time, all of those things, because once you get out to the site, you're going to want to throw those segments up as quickly as you can and get that bridge done. So everything that you do in the casting yard from a quality standpoint just helps that later on. So let's talk about production rates. I mentioned that our goal is always for typical segments to have a 1 day per segment per bed production rate. This is a very typical rate. It's very achievable, of course, after the learning curve. And this is the kind of segment we're talking about, relatively straightforward, not a lot of blisters and blocks and things in it, but this is a very achievable rate. Typical segments with anchor blisters might need a little bit more time. This might require a swap out of a panel for the core form to make this happen, but these are smaller panels, so it's not too bad. And typically you can get these segments 1 day per segment per bed. When you start getting into deviator segments where we are taking internal or external tenons inside the box girder and all changing their angles at certain locations, now you're looking at much larger blocks. This requires basically a full swap out of the core form panel. It requires some more time to tie the rebar for the cage and that sort of thing. So there's a lot that goes into that, and these will typically slow down your production rate to about 2 days for a deviator segment in each bed. So just something to consider. And then variable depth segments, the same thing. Simple variable depth segments, you can usually cast those, one day per segment, but some of the more complex ones and some of the larger ones, perhaps, it might take you a couple days per segment to get that done. And again, these are sort of typical production rates. Your mileage may vary depending on the complexity of your project, the detailing of your blocks and diaphragms and deviators. And then, as I mentioned before, the pier segments and expansion joint segments that have the big diaphragms in them, that sit over the piers, those are complex. They take a long time to tie. And really, you're looking there at, working offline in specialty beds. And these are often 4 to 5 days per segment. It's not at all unusual. So just something to consider. So in August, we're going to talk a lot more about precast segment production, and you're going to get the contractor's perspective on setting up casting yards and all of the details that are involved in that. There's going to be a lot more discussion about the geometry control process. So to learn more about the whole segment production topic, I highly recommend that you attend that seminar. So now that you've got your segments produced, we've got to put them up. So the simplest and most common way, I guess, of doing precast segment erection is the span by span technique. And this is relatively straightforward. We're going to take all the segments out, put them up on some kind of temporary support equipment for the entire span, post-tension those segments together, and then at that point the span is self-supporting, and we can move to the next span down the line in a very repetitive, very linear fashion, and build span by span. So this is commonly used for long bridges over water where we've got, a lot of relatively reasonable span lengths. Urban areas, this is really common for highway viaducts, and now in the last 10 years, light rail elevated viaducts have used this technique extensively. Basically any large project where you've got a lot of similar repetitive spans with repetitive details that really help you get over the learning curve quickly. Anytime you're building in a sensitive environment, whether it's environmentally sensitive or sensitive because of maintenance of traffic, and building from above is an advantage, this is a great technique, and it's extremely fast. From a cost standpoint, it's actually historically has competed very successfully against alternate structure types, steel girders, pre-stressed girders, etc. And back in the day, Federal Highway mandated concrete and steel alternate structure types in the plans for major projects, and when that happened, span by span segmental competed very, very successfully against other structure types. So something to consider. Obviously those requirements aren't there anymore nowadays, but it's definitely something to consider. Super fast construction. These bridges tend to have very repetitive details. The technique is the same over and over again for each span. Obviously, you're eliminating the forming and reinforcing and pouring of concrete cast in place decks out on the site, so that speeds up the span construction immensely. Really for simpler bridges with sort of typical span lengths, and with some of the simpler erection equipment that's out there, 2 spans per week is not at all unheard of. That can be very achievable once you get over the learning curve. So that can result in significant MOT savings and really minimize user delays quite a bit. This is a great example. This is the JFK AirTrain Light Rail project in New York City. This is the Van Wyck Expressway in Queens. And the contractor here is using precast segmental span-by-span construction to erect the light rail elevated viaduct right down the median of the Van Wyck Expressway. Tons of traffic, lots of MOT, and traffic is flowing very smoothly throughout the process. Another advantage is that we use external tendons primarily for span-by-span construction, and this allows us from an engineering standpoint, from a design standpoint, to have really good ductility for our spans, which is great at ultimate load levels, which we hopefully won't ever get to. It also means that the segments are quite a bit easier to construct because it eliminates internal duct work, duct couplers, all the little details for building segments that have internal PT tendon ducts in them, which means that casting is easier, and also tendon installation is quite a bit simpler because you're doing it inside the box girder and it's relatively easy to see everything and manipulate everything. So, and this also simplifies inventory inspections. As an owner, this is a great option because you can basically visually inspect almost the entire length of your tendons inside the box girder. So it's a great advantage for span by span. And of course, paying attention to the aesthetic details, you can really come up with some very aesthetic structures using span by span technology. So looking at a typical sequence, we'll use the example of a 4-span continuous unit. This is very typical for span by span for highway bridges. You see here we've got an expansion joint location marked in yellow at each end of this 4-span unit. And as I mentioned before, because the pier segments and expansion joint segments are cast offline in their own cell and not match cast against the typical segments, we do have cast in place closures at each end of each typical span. So that does a couple things for us. It helps with that casting yard casting schedule. It also helps us to have minute amounts of geometry control and geometry adjustment of our spans out in the field during erection. Here's the typical external tendon layout. Again, this is external to the concrete, but internal to the box girder interior. And you can see here that for a typical layout like this, our tendons start high at the pier and expansion joint segments and then deviate down through the deviator ribs and then back up again. And that allows us to counteract the dead and live loads in the most efficient way possible. First step in the process is to erect the segments on the truss for a typical type of span. And really the first segments that need to go in are the pier segments that are out at the leading edge of the erection front, so away from the previously completed spans. If you have an underslung truss like is shown in this picture, those can either be directly crane erected at that location, or they can be set down on the truss and then rolled out to the end of the span, just like the typical segments are. For overhead gantries, this gets a little bit more complex. This particular overhead gantry has a system where there's a temporary front leg that sits offset to the pier, and then the pier segment pair is lifted up into place on top of that pier cap with manipulator arm. Those two segments are epoxied and post-tensioned together, and once that is stabilized and jacked underneath, then the main leg of the gantry then is transferred up to sit on top of those pier segments for erection of the rest of the segments in that span. It's a fairly complex process. It can take, 1 to 2 days to accomplish that, and get everything ready to go safely for erection of the span. So a lot of times with overhead gantries, contractors will actually choose to crane erect their pier segments ahead of time and set them on top of the pier well in advance of the progress of the overhead gantry that's building the typical spans back behind the erection front. So it's a great choice. It really eliminates a lot of the complexity and many of the steps in the erection process for an overhead gantry. Once the pier segments are up, we'll put our typical segments on the truss, either with a ground-based crane lifting them directly on, or a lot of times we'll have a crane sitting on the deck itself and deliver segments from the previously completed spans. And sometimes there are some really interesting specialty segment lifters that are used. This was on the 183 viaduct in Austin, Texas, back in the 90s. And this was a really interesting system that the flatbed trailer drove a segment up, kind of backed it up underneath this thing. It picked up the segment and turned it 90 degrees and then set it down on the underslung truss. And it was very efficient because it didn't have to pick the segment up and lift it out very far. And then if you've got an overhead gantry, erecting segments mostly occurs from the ground. The segments are delivered directly underneath the span and then lifted into place with a manipulator and set on the temporary hanger bars. And a lot of gantries also have the capability to deliver segments from the rear, from the completed spans, and pass those segments sort of sideways through the rear leg. Once all the segments are hung from the truss and we've got all the deflection out of our erection system, we will begin the alignment process. We'll typically line and grade the first segment in the span closest to the completed span that we're standing on. And then we'll start the process of applying epoxy to each of the joints, lining up the subsequent segments, and getting them all lined up and epoxied together. So keep in mind that when you're working over traffic or in an environmentally sensitive area, you want to have tarps there to take care of catching any of that excess epoxy that squeezes out of the joints during that process. So we always want to apply a minimum pressure of 40 psi across our cross section during the epoxying process. For span-by-span bridges, that's typically done with temporary PT bars running through temporary PT bar blocks. Here's a shot of a gentleman with a center hole PT bar jack stressing some of those temporary PT bars and getting good epoxy squeeze on the segment joint back over here on the left. You can actually see it squeezing out of the web wall. Once all the segments are epoxied together and temporarily PT'd to keep that epoxy pressure in there, then we can form up and pour the closures at each end of the span. And this is typically done by blocking up each of the closures and then installing one pair of the external tenons inside the box, stressing that pair to about 10%, which locks everything together, locks the head pier segment to the typical segments, and in turn, the typical segments to the previously constructed span, and then everything's nice and stable for us to place concrete for these closure pours. Once we reach about 2,500 PSI on those closures, typically, but as per what's shown in the design plans, we'll stress the longitudinal post-tensioning, and at that point, the span is self-supporting and we can release the truss and move forward. For overhead gantries, a lot of times these access platforms are literally hung from the front end of the overhead gantry, so that's kind of a convenient spot to be able to work from. But these jacks are heavy. they weigh a couple thousand pounds, and so you've got to have a system to manipulate those jacks and move them around from anchor to anchor. And we're always stressing from the leading end, well, almost always, but we should be stressing from the leading end of the erection front, which makes it the easiest to access those tenon anchors for stressing. Then we'll release the truss and launch it forward to the next span. So there's a variety of equipment here that can be used for this. This is probably one of the simplest pieces of equipment. It's an under soffit truss. The advantage of this is that it's really simple to move it from one span to the other. It's just got a single pick point hook, and once the span is completed and you're ready to move this thing, the ringer crane simply picks it up, sticks it on the barge. They move the barge over one segment length or one span length, and then set this thing back up again. It's like a 1 to 2 hour launch process. It's about as easy as it gets. The disadvantage is that it's really difficult to use this system for spans that change in length. So it's great for a bridge like this where every single span is the same length, and therefore it doesn't need to have any length adjustment to the truss itself. The other common option that's very relatively straightforward is the underwing truss system, or underwing box beam, as it is in this case for the Honolulu Light Rail. This is a great system. The segments are sitting on the truss, and of course you've got to design your segments to handle the negative moment, or I guess it's the positive moment in the wings here from the segment weight itself sitting on those support points. And then as we sort of get into more complex systems, there's a wide array of overhead gantry systems on the market. This is a gantry built by Structures. This is probably one of the simpler overhead gantries that's out there, but the advantage of this is that you can work almost completely from above, and you don't have to worry about vertical clearance underneath the erection system, especially if you're in an urban area. So it does have its advantages. It is more complex to launch forward, so it does kind of slow down the overall erection process a little bit. And there have been some variations over the years, most notably, and has been used several times, is erecting segments on falsework towers. And probably the pinnacle of this is the I-59, I-20 project in Birmingham, where the contractor had an interesting situation. AlDOT decided to basically shut down the entire interstate through the central part of downtown Birmingham, and that allowed the contractor to build span by span segmental, but build it with a series of 8 spans worth of shoring towers. And through some careful planning and sequencing, the contractor was able to achieve an erection rate of 172 spans in 217 days, which honestly is, I don't know if anybody will ever beat that. That is absolutely sort of best case scenario with best access and really, really good planning. So, kudos to those guys. They did a fantastic job erecting at an extremely fast rate on that project. So in Seattle, we'll learn more about span-by-span erection equipment, dive into some more of the details of that erection system. We'll talk a little bit more about the erection geometry control. So there's more to come in Seattle. Then the other method that's commonly used for erecting precast segments is balanced cantilever erection. Now here, we're not using a support system that holds the entire weight of the span up at one time. Instead, we're starting at the pier, working our way outwards in a balanced fashion in both directions, and that means that the bridge itself is supporting its own weight plus the weight of the erection equipment during that erection process. And that allows us to sort of go beyond the limitations of the erection equipment and really get into some much longer spans. So we're going to use that in areas where we need longer spans than span by span can achieve. This often happens in congested urban settings, and especially where we have tight radius curves like the I-4 connector in Tampa, Florida. It's also a great choice when you're in sensitive environmental areas where you want to really stretch out your span lengths and minimize the number of piers and foundations that are impacting the environment, or if you're going over a deep valley where it's just simply difficult to get a lot of foundations in, or the cost of your substructure is very high. And then in some cases, it works out great for water crossings like the Bonner Bridge in North Carolina, where there was a desire to stretch out those span lengths to allow for tidal flow to come in and out of the area more or less unimpeded. So it really is a great option for those longer spans and more complex geometry. So when we're talking about span by span segmental, really the practical range is in the range of 100 to 180 feet max. 180 is a little bit rarer, but is actually currently being done at the Harbor Bridge in Corpus Christi right now. But for balanced cantilever segmental, you can really stretch those span lengths out anywhere from 250 to 600 feet if you've got a variable depth box girder, and that's not at all uncommon. So the segments are a little bit more complex because now we've got internal PT in the top slab and in the bottom slab. We need the top slab tendons for as we're cantilevering, and then we need the bottom slab tendons for making continuity when we complete the cantilevers and tie the spans together. And there's been a variety of different box girder shapes that have been built with precast balanced cantilever over the years. You get the typical trapezoidal box. You've got a 2-cell box, 3 webs, which is quite a bit less common, a little bit more complex. Sometimes you're in a situation where you're, say, in a gore area or something similar, where we have erected in balanced cantilever coming off of one pier with 4 cantilevers. So you've really got to balance all 4 cantilevers to keep the forces on the substructure down. And then this was a really unusual application at the Ringling Causeway in Florida, where they needed a really wide cross section, and so they had a 3-cell box that was very large, but it was really impractical to lift and carry segments of that size, and so they split the superstructure into 2 halves and have longitudinal stitch pores running down the middle of the bottom slab and the top slab. So that's a very unusual application of the balanced cantilever precast erection. But the basic sequence starts with placing the pier segment on the pier, and then we achieve some kind of moment fixity or rotational stability, either by making this a monolithic connection, or by putting in some supplemental supports like a temporary tower or maybe a prop somewhere. And then we'll erect our typical segments. The first typical segment goes in and it's post-tension to the pier segment with some temporary PT bars. Then its opposite pair is installed to make things balanced. And then we'll install cantilever tendons running through the top slab to tie that system together. Now, you'll notice here that this is basically a symmetrical system about the center line of the pier. And that's very typical for precast balanced cantilever systems. The pier segments are very complex. They can be either cast in place or precast, and if you have a variable depth box girder, which you really need for the longer spans, these can get to be very big and very heavy. So it's very common for these to be split into 2 halves and then post-tensioned together out at the site to reduce that picking weight. You can see here all the temporary PT bars that are tying these 2 pieces together. And then also this one is unique because only a portion of the diaphragm was poured at the casting yard, and the rest of this diaphragm will be completed after these vertical tendons that tie the pier segment system to the foundation are installed. So all in the name of trying to keep that lifting weight down as much as possible. It's very common, although not necessary, to have a closure pour between the pier segments and the first typicals on either side. It just depends on the designer's preference or the contractor's preference. But the nice thing about a closure pour here is that it does allow you to do some fine tuning of your geometry for that starter segment in the cantilever, so that you can just have that much more assurance that you're going to end up where you think you're going to end up at the end of the cantilever erection. So our erection proceeds in that same manner, where we're basically installing pairs of segments, 1 on each side of the cantilever, keeping everything no more than 1 segment out of balance, and then stressing cantilever tendons as we go. And geometry control is really crucial during this time. All the segments were precast together at the casting yard, so you know the theoretical geometric relationship between all the segments, and when you put them back up at the site, it all should go back together, the way you expected. Also accounting for the loads and demands on the bridge during the erection process. We can talk about shims. It's a little bit of a sticky subject, but you do have some ability to install very thin shims in the segment joints to make corrections if needed. But it's all just underscores the need to really do a good job with your quality control in the casting yard and really pay attention to that geometry control. But we'll track this and survey this at every step of the erection operation to make sure that we're tracking in line with what we expected. Epoxy is placed in the segment joints just the same as with a span-by-span bridge, and we'll use PT bars to apply that squeeze pressure across the joints and get that nice even squeeze, evenly thick layer of epoxy between the joints that's needed to make that epoxy perform properly. There's a couple different types of PT bars for precast balance cantilever that are pretty common. Probably the most common is to use internal PT bars running through the top and bottom slab like these. And what's great about these is that they actually can contribute to the permanent PT capacity of the bridge when you're done. So that's a nice system. It takes care of the epoxy squeeze, but also helps out with, say, ultimate moment capacity. Although it's also very common to use external temporary PT bars as well for precast balance cantilever, similar to the span-by-span. And then the permanent PT, the cantilever tendons are installed. They run through the top slab in the ducts and then anchor out either at the segment joint at the interface between the web wall and the top slab, or especially in more corrosive environments, we'll anchor those in blisters that are in that armpit area between the web and the top slab. And then as we progress out, we've got more and more cantilever tendons that are placed in there. And of course, at the location of the pier segment is where they all pass through in that top slab. So you've got a lot of PT in that pier segment area. Again, you've got a plan for access platforms and ways to lift your multi-strand jacks into place to stress those tendons. Here's what you end up with is the cantilever tendon layout. So you can see here that at the pier, you've got all of the cantilever tendons passing through that pier location, which makes sense because that is the location where your maximum negative bending moment during construction is. And then as we get done with the cantilevers, we've got to make a continuity closure and either tie the cantilever into the abutment area or tie two cantilevers together. And again, as we're doing our geometry control and tracking everything during erection, it's really important because most of the time these closure pores are really only a foot or two wide. So there's not a lot of room for error. There is some adjustment capability that is inherent in these bridges, but that can be accomplished with either counterweights or adjusting the cantilever by jacking it. But all of these things, when you make continuity here and if you're jacking it or putting counterweight up there, that load gets imparted into the structure permanently. So you've got to coordinate all of those efforts with the engineer to make sure that the permanent stress condition of the bridge still meets code requirements. Hopefully you've gotten really close. The alignment of your cantilevers is very, very small. And we can use strong back systems here with PT bar jacks to make those minor adjustments and then pour the closures. And then we'll stress our continuity tendons. There'll be a series of these similar to the cantilever tendons, and these continuity tendons anchor in the bottom slab blister blocks. All right, so a couple of project examples here, urban interchange in Dallas and a long span crossing over the river in New Jersey. So there'll be more details about this in the August seminar. If you guys want to see more about balance cantilever erection and post-tensioning details, and we'll cover topics involving cable stayed bridges as well. And then finally, cast in place balance cantilever erection. This is similar to precast, except that instead of precasting the segments and shipping them to the site and putting up, we're using form traveler systems to build our cantilevers in situ. It's a really versatile method. It's got a lot of flexibility. You can do all kinds of different cross-section shapes and aesthetic treatments. And we can really get some good long spans here. We actually can go longer than precast, get up to 760 feet with all kinds of different geometric ability there. Great option for deep valleys and environmentally sensitive areas, especially areas where it's really hard to lift segments into place that are precast. The key to the process here is the form traveler. This is a movable form system that supports itself by anchoring into the previously cast segments in the cantilever, and the form system hangs out over the front and carries the forming system out in front of it. This thing is fully launchable in a kind of a two-stage process. We'll slide these launching girders forward and then roll the entire system along those launching girders to put it into the position for the next spot. Cantilever tendons layout is very similar to the precast system, as is the continuity tendons. The difference here, though, is that instead of a symmetric pier segment, we have an asymmetric pier table, which is the most common way to do these. And the reason for this is we want to have, first of all, we've got to have room for both form travelers up on the pier table. And we also want to try to limit our out of balance forces to no more than about a half a segment. And this is a great way to do that. The pier tables are fairly complex pieces of the bridge, and they're typically placed in 3 lifts because of that complexity. So after the formwork and false work is set up, we'll cast the bottom slab, and then we'll cast the webs and diaphragm together, and then finally the top slab, which has got a lot of PT in it, running through longitudinal cantilever tendons. You've got inserts for the form traveler tie downs, etc. The pier table construction is really a significant portion of the overall schedule duration for building the cantilevers. I was on a job in Tennessee where we had 5 segments on each side for the cantilevers, and so there weren't very many segments, and the pier table was easily about half the overall time for building the cantilevers. For longer cantilevers with more segments in them, that pier table can still be 25 to 30% of the overall duration. They're very complex, take a long time to get up and put in place. But once they're done, the form travelers are installed. These form traveler systems are fully adjustable to achieve any variation in the geometry that you want. And the typical casting cycle is about 1 segment every 3 days. So you spend the first day looking at perhaps form traveler A, you spend the first day aligning the bottom deck, putting in bottom web wall, bottom forms. The second day, you're putting in the rebar for the bottom slab and the webs. You're advancing the core form and putting in the top slab bulkhead forms. On the third day, you're tying in the top slab rebar and the ducts and prepping everything for pour. So then you're pouring on the 4th day. So you poured on day 1 at Traveler B, you poured at day 4 on Traveler A, and you're going to take about a day to cure that segment up to about 4,000 PSI, so you can stress the longitudinal tendons, and then you're stressing the longitudinal tendons and launching the Traveler forward on that 6th day. So on day 7, you're back to pouring at Traveler B again, so it's about a 1 segment every 3 days cycle. So again, we've done some pretty wild bridges with cast in place balanced cantilever. Pearl Harbor Memorial Bridge had a 110-foot wide box girder. It was a 6 web box. And the Kanawha River Bridge in West Virginia stretched the span lengths out to the max that has been done in the US at a 760-foot main span. So there'll be more details on cast in place segmental erection, and a lot of great information on contractor perspectives, and we're going to have an awesome panel discussion on owner perspective at the August seminar, so hopefully everybody can join us. And with that, I will, we can switch to the question and answer session now.
Hey, thanks, Wade. Greg Freeby here. We are running a little bit past the hour, but we do have a couple questions that I think warrant folks warrant us entertaining. So let me just quickly introduce our Q&A moderator is Mr. Tim Berry with RS&H. He's been with them he has more than 20 years experience with a number of segmental bridge projects in Florida and Virginia under his belt. He's currently chairing the grouting committee, the ASBI grouting committee, and was the past chair of the ASBI construction management practice group. So with that, I will turn it over to Tim because we did have a few questions come in that I want to hit if we can before we sign off. And to you attendees, if you need to bail out, certainly I respect that. We probably have just about maybe about not even 10 more minutes here with Q&A. So Tim.
Yeah, sure. Thank you, Greg. So Wade, one thing you talked about balanced cantilever, span by span, and cast in place. Have you seen, is there if all else is equal, is there a preference to any one of those types, or is it really just driven by site conditions and the type of bridge?
Yeah, that's actually there's a lot that goes into that decision-making process. A lot of it is driven by the characteristics of the site. The thing about precast versus cast in place is that you've really got to look at whether your project is large enough to justify the upfront cost of building a casting facility, pre-producing those segments ahead of time, that sort of thing. That's a fairly sizable capital investment, but it can pay off in the overall speed of the operation. For smaller projects where there's a smaller number of segments, cast in place, may be a better choice.
Okay, interesting. As far as speed, is there one type that you've seen faster than the other, or is it again just dependent on the individual structures?
Yeah, generally precast. If you had two cantilever bridges and one was precast and one was cast in place, the precast bridge could be erected much more quickly. Just simply because you've done most of the work of building the superstructure, offline ahead of time while the substructure was being built. So, that is offset again by the capital cost of putting a precast yard together. So it's not an easy solution, and the designers will often debate quite a bit internally before deciding on one or the other.
Absolutely. Okay. I had a couple questions about camber. First one in regards to cast in place. How is camber factored in during the erection process and ensuring your geometry control?
Well, so you have a camber curve which represents the final deflected shape of the structure at the end of all time-dependent effects: shrinkage, creep, steel relaxation. And then you take the inverse of that deflected shape, and that is your final target. But there also are a series of individual targets at each stage of the erection process. And as you can imagine, as you add a segment on either side, the bridge wants to tilt over towards where that segment got added. And then when you add the segment on the other side, the bridge tilts back the other way. When you add a segment, the cantilevers droop a little bit. When you stress the cantilever tendons, the cantilevers pick back up a little bit. And all of those individual steps in the erection process are calculated ahead of time by the erection analysis and provided to those of us out in the field that are monitoring the geometry control. And we combine each of those, what we call phase deflections, together with our target camber curve to come up with where we want to set that form traveler for the next segment pour.
Okay, great. Yeah, it's certainly it's an intricate process, and certainly one of the more important parts of building these structures. That covers the questions that we had from the audience. Thank you, Wade. And again, I'll put in my own plug for the seminar coming up in Seattle. This is just a part of some of the some of the topics we'll cover there. So, Greg, with that, we'll turn it back to you. Thanks, Wade.
All right. Well, thank you, guys. Great presentation, Wade. Appreciate the level of detail you were able to cover in a short period of time. So, thank you. Again, Encourage folks to sign up for the seminar if you've not. We will be doing, of course, our monthly webinar again in August, and I think I showed you that topic earlier when we were talking about the Manhattan West deck project. So with that, we will sign off, and everybody have a good day.